Right, yeah.
Well, the recording is on, so if you want to say hi, Mom, you can go ahead.
Hi, Mom.
Hi, Mom.
But am I seeing the contradiction?
I think I'm stuck on tel too.
I'm actually, yeah. I mean, I've got a whole bunch, so there's like not I have like more than that's what I'm doing. Don't jump to conclusions. This is all things I pulled out of the resolution.
Right. Then I changed my mind.
That's it. It's not hard.
All right. So we are back to, yes, go ahead. Roll sheet. All right. Somebody remind me, and the recorder is on too, so I'm going to double check that too. Well, I'll pass the roll sheet first, and then I'll go back. No, it's all batteries. Someone has 2 AA batteries, that I can borrow. We can get the mic going.
I have one.
You have one? That may not work.
Well, if anybody else has one.
Yeah. Next time I'll bring some from home, because I got a whole bunch of rechargeable from home.
You don't always keep one on you for emergencies?
Well, you know what? I think I have one too. I have one
really?
rechargeable, so that would
What's the size battery?
AA.
I got some good ones here.
Some good ones.
I got one from my flashlight. Oh, this
Take
feels
it out of my
These
USB.
are really heavy.
okay. Thank you.
They're rated out like.
Just remind me to give it back to you. Okay?
Sure.
All right. I'm pretty sure I'm working out of classification here. Oh yeah, these are really good ones. They are
Made in Japan.
made in Japan, and it's not Sony. It's Panasonic.
Yeah, I actually just found them, and then once I looked at the rating, how much milliamperes it can hold, I was like, wow.
Yeah. Okay, that's good. Well, thank you. All right. So, are there any questions about resolution? The homework about on resolution. I saw a few people earlier today. Yes, go ahead.
Are we supposed to be doing things besides resolution? Is it just resolution where we're applying like over and over?
The homework assignment is about proving a theorem. So you have to use resolution as a mechanism to prove a particular theorem. So there is a particular expression that I want you guys to prove, and the question is, how do you do it by resolution?
Okay.
Okay? Yep.
Are we required to do the single underline, double underline thing?
That will help me understand, so if you can do that, that'll be great. But if you can't figure out how to do it, I guess it's okay too.
I can't underline in Notepad, so.
Notepad?
Because I have to translate from Notepad.
Oh, but you can, well, once you get into here, you can right click and, actually learn how to do the double underline thing. So, I know it's not going to be, it will be a little bit ugly, because underline, it's not that ugly. It's just underline, underline.
Okay.
So you're underlining something that already has an underline, so that will give you the double underline. But you need to use the curly braces to kind of group the stuff that you want to, use the underline. So, but it's not too difficult. Okay. Any other questions? Okay. No other questions? Any questions about why this stuff works? Because that's the more important part. Yep.
Oh, we're talking about the technical part, right?
No. You can ask any question related. Go ahead.
I'll ask later. It's okay.
Okay, just remember. Okay, go ahead.
I was curious in the resolution when you get down to the script, and 0, so it's false. Is there
For this one?
Yeah.
No, this is really just the result of resolving this R, which is by itself an expression, and this not R, which is also by itself an expression. So when these two expressions resolve, there's no leftover term from either one, and that's why you come to a false. And it's really just another step of resolution, except the result of the resolution is false. And when you get to a false as one component of a huge, gigantic conjunction, the whole conjunction is false, and that's how you get to a contradiction.
I was just checking, like when we're doing CNF, you want to say like the Morgan's law.
No, there's no need to apply, to write any, to document the law that you're applying, because with this homework assignment, the only law you'll be using is resolution. Every single step is resolution. That's the point of resolution, because instead of having all those other transformations, remember, okay, let me just kind of go back to the previous lecture note. So just so that we can compare, I will open it in on another tab so we can go back and forth a little bit. So with resolution itself, which is only this part here, resolution itself is one inference rule. Okay? It's just one single inference rule. And yet, if you can express everything else in a CNF, this is the only inference rule you need to know to prove theorems. Okay? So that's where we are at this point. That's what you're doing with your homework. And that's why we are translating everything into CNF first, is so that we can apply resolution, resolution, resolution. And eventually you will either come to a point where you say, oh, we have a contradiction, okay? So the theorem has to be true to begin with. Or you come to a point where you cannot derive any other expressions, and yet you cannot get to a contradiction. Then you give up and say, okay, this theorem cannot be proven. Okay, you first and then you. Okay.
All right, so we're using the previous assignment CNF, and we are going to infer that it is not S implies not Q. Is that correct?
Correct. Yep, go ahead.
So this assignment depends on us having done the previous assignment correctly, correct?
But I said that you can use my solution.
I got it.
You posted that?
Yeah.
It's on YouTube.
It's on YouTube, so you have to go to YouTube and
Okay.
start with my resolution. I mean my CNF answer. But it is on YouTube already, so you can just kind of copy that.
Just pause at like 12 minutes.
Timestamping. Okay.
So, I think this question is a little bit more about proof techniques. So,
Techniques, okay.
One of the ones that we talked about was proof by contradiction, where we had a bunch of conjunctions.
Yeah.
And then we tried to force one of them to zero. And then the conjunction of anything with zero becomes zero.
Yes.
But is it also a method to have a bunch of disjunctions where one group is true and one group is one?
No, you cannot do that. When you use disjunction, there's no resolution to do it. Because resolution only works when you have a CNF. Because it only works, it has to do with this part here. The only reason why resolution works is because of this. When you have a general form of two well-formed formulae, okay? So when you have phi or psi as one, and then you have not psi or rho as the other one, and you have a conjunction between these two, I can prove, using logic, I can prove that you can imply that phi or psi, phi or rho has to be true, okay? And this is based on logic. Yep, go ahead.
So I understand that portion, but I was talking about like on the screen there, where it has one disjunction with other things.
Yeah.
And that can be simplified to true. So is there a certain name for that step, or
For
the very last step on the
For the last one, this one here, you mean for this step to become the final solution, which is just true? I don't think there is a particular name for that, because this one is really just, if you look at the truth table, what it is you have a variable x that can be true or false, and then you have the expression 1 or true or x, right? And then for each row, it is a true, because if one side of a disjunction is true, the whole thing is true. So that's why, that's why it works. I don't know of any particular name, that states that particular one.
So we don't have to worry about justification for that stuff, or for like 0 and some other term. We don't have to worry about justification for that. We just
Correct. You don't have to name the simplification. Yep, go ahead.
I would just say like definition of conjunction or disjunction.
Yeah, ultimately it goes back to the definition. It's because of the definition, but there's no specific name for this one. Well, maybe somebody has a specific name, but I don't need you guys to refer to that. Okay, so what I want to do is to go back to here and say, if you only have a CNF, if everything is expressed as a CNF in a particular system, this is the only one inference rule that you will need to use for everything, okay? As opposed to the stuff that we talked about before, okay? So remember this stuff that we talked about before, and we talked about all the inference rules. So we started off with something like this, and then we also talked about this. So we have a whole bunch of inference rules in general logic. Is that okay? Because these are all applicable when you want the computer to do things the way that you do things. Because that's how we do things, okay? We understand the law of commutation, we understand double negation, we understand all of these things. So in order for a computer to do things the way that we do things, you have to capture all of the rules that we use in logic, in Boolean algebra. Put everything into inference rules so that the system can use this. Is that okay? So you have a lot of rules to encode in this case, right? And you can end up with a lot of products that you throw back into the set of well-formed formulae that ultimately doesn't do any good. Is that okay? There's no upper bound anymore. Well, why did I say there's no upper bound? Because you can keep multiplying stuff out of nowhere because of certain types of production. What kind of production are we talking about? We're talking about this guy here. This guy basically says, out of nowhere, okay, you can claim that a particular well-formed formula or the negation of that well-formed formula is going to be true. You throw the result back into the pool of well-formed formulae. But how many well-formed formulae can you form out of a fixed number of variables? Some people may say, oh, but we went through that calculation last time already, it's finite. But in this case, we don't have a finite number because you can come up with, okay, P, which involves just one single variable, is a well-formed formula. Okay, cool. What about P and P? Well, it is still P, but it's another well-formed formula. I keep attaching a conjunction to it, and this can get infinitely long. So we keep throwing stuff that is useless into the system, and they don't do any good, and you don't know when to stop. Are we doing okay so far with that discussion? So when we try to get a computer to do things that we do things, we can run into problems because computers do not have intuition. It doesn't look at things and go like, oh, that doesn't make any sense. Okay, why would I want to keep doing something like this? The computer doesn't understand. It just say, okay, what rules can I apply? Oh, that first rule, I can keep applying that over and over and over again until you run out of memory. Is that making any sense? As opposed to resolution, or the use of CNF and resolution. This is the only rule that you use. But we have already proven that using this particular rule, you cannot make things end longer and longer and longer. It cannot get longer and longer indefinitely. At some point, they basically have to reduce and become smaller and smaller. There's an upper bound of how many well-formed formulae you can possibly get into using this particular inference rule. Okay, so there are two reasons why we want to use CNF and resolution instead of the other type of inference, which is okay, because in CNF and using resolution, one, there's only one rule to apply. And two, the problem can be solved in a fixed number of time because you can only have up to 3 to the power of n, and n is the number of n is the number of variables. This is the upper bound, Okay, if you have 6 variables, then you can have up to this many well-formed formulae. You cannot have any more than that. Now, this is not a tiny little number, but nonetheless, it is finite. The other system can possibly give you an infinite number of well-formed formulae, most of which are useless. Okay? And then the last reason is resolution is inexpensive. It's very easy to apply from the computer's perspective. Because what you're doing is just looking at the expressions, the disjunction expressions, and say, oh, this guy has got one variable. Then you look through and find out that, oh, this guy has got a negation of the same variable. These two have never been resolved before, and they have never been used in a resolution before. So combine these two, come up with a new expression. But then you can then tag that these two have now been resolved and not to resolve it ever again. You can remember that so you won't get into a loop. So that's the reason why resolution is so useful, because from the perspective of automating theorem proving, this makes things so much easier. Yep.
I remember when last class you told us the 3 comes from the other one that's missing. How would it work when it's missing?
You get false. That's the case when all n variables are missing, including the negations. Now, is that okay? I'll give you an example. Let's say we have 2 variables, p. Oops. Okay, that's.
Danger zone.
It just doesn't do very good when I walk over there. So let's say we have 2 variables, p and q. Okay. So according to that, we have 3 to the power of 2 possible ways to combine these two, right? So we have p by itself, q by itself, and then we have not p by itself, not q by itself, and then we have p or q, p or not q, not p or q, not p or not q. So there are 8 of these. And then where do we get the other 2? There's only one more, which is false. Because false is just not having anything. Because you can look at each and every single one of these and just say there's an implicit or 0, or 0, or 0. This one just doesn't have anything and it's just 0 itself. So that's why there are 8 possible ways to write disjunctions out of 2 variables. Yep.
But what if we had 3 variables? That means we would have 2 falses?
No, because if you have 3 variables, let's say you have p, q, r, right? Then you can have 3 to the power of 3, which is 27. How do you get to 27? Well, I'm not going to waste my time. But instead, I can say, one way to do that is to do an r or this bunch of stuff. Then you have not r or this bunch of stuff. What is the last one? You have false or this bunch of stuff, but since false or doesn't do a single thing, that means we just have this bunch of stuff. But nonetheless, there are 3 of those, right? This will give me 9, this will give me 9, and then there's the original 9 without r at all. So that's why I come up with 27. Is that working?
Yeah.
Well, before you ask this question, it never occurred to me, how to do all the counting and how to prove that it is actually 3 or n, 3 to the power of n. But now that I worked this out, it's actually pretty easy to prove it. At some point, someone can remind me to prove this by induction, because this is a very typical way of proof by induction. Is you prove a base case, and then you say, okay, from one step I can go to the next step. Then it can go indefinitely. So when we get to proof by induction, remind me again of this particular number. Yep.
Just kind of nitpicking, but your 0 is supposed to be circled there as well.
Yeah.
Say again?
The 0 should be in
or
false.
0 is part of the set.
So you have R and not R
I'm just
and false.
nitpicking. It's not that important.
What?
It's supposed to be within the circle.
Oh, the circle is supposed to be in here.
Yeah.
Okay. The false is supposed to be in here because it is one of the 9 expressions.
Yeah.
Yep. Okay, very good. Thank you. Okay, any other questions? So are we okay in terms of, do we understand why we study resolution? First of all, why do we study propositional calculus? Because we want computers to do all the proofs so that we don't have to do it. Okay? So it's very mechanical, it's based on syntactical manipulation, and but it has to mirror what we actually do in mathematics and in logic. Okay? So in other words, it has to be sound, it has to be complete. And then we look at all those rules, okay, from the previous slide, and say, wow, that's a lot of rules, and we can come up with nonsense well-formed formulae that really doesn't do any good, but we don't know when to stop. Okay, so we think about that and go like, that's bad. Okay, so we think about that a little bit, and then we come up with the mechanism. Some smart person, not me, came up with resolution and go like, hey, if we can transform everything into a long CNF, then we only need one rule, which is resolution. And using resolution, we can only come up with a fixed number of well-formed formulae in the big huge conjunction. It is 3 to the power of n, or n is the number of variables. So it's finite. That's the great thing about this. And then the second thing is that rule is really easy to apply. All you're doing is searching for a variable in one term, the negation of the very same variable in the other term, combine those two. Concatenate the leftover stuff, make it a new term, attach it to the end of the new conjunction. That's it. So it's very easy to do, it's mechanical, it has an upper bound in terms of execution time, and it works really well. So that's why that's the progression of all the topics and how they connect. Are we doing okay so far with that? Okay, all right. So we'll go ahead and do one more thing that is related to the homework assignment. And what I'll do is I'm going to show you P implies not Q, okay? So let's say this is what I want to prove. If I want to prove this, then I need to put the negation of this into the CNF that represents the rest of the knowledge of the system. So we need to negate this, okay? The negation of this is fairly easy to do. The first thing we do is we say this is not P or Q, and then we negate that. And this requires us to use De Morgan's law, because the negation is applied to the disjunction. So we have to do De Morgan's law to move the negation into the inside. So now we have double negation P and Q, or not Q, excuse me, double negation P and not Q. Double negation cancels out, and we end up with just P and not Q. So now the question is, does that make sense? Is that really the negation of P implies Q? What do you think? What does P implies Q mean?
Q or P or not Q?
It's not P or Q, which also means when P is false, we don't really care about Q, but when P is true, Q has to be true. So the negation of that is basically saying when Q is true, P has to be true. Let me see. No, I take it back. When Q is false, P has to be false. That's the other way. Well, that's still implication. We are saying, well, P and not Q is the negation of that. So if you plug in P being true into here and Q being false here, that will turn the disjunction. It will turn the implication to false, and that's why it is the negation. Is that okay? Yep.
So you would just add that onto the CNF?
Whatever CNF you have, due to iota, you just make a conjunction. The bottom line is you have to turn this thing into a CNF first. If it is already a CNF, then you can attach it to another CNF by a single conjunction. Okay?
Why are you negating it?
Because it is proved by contradiction. So the very same thing that you want to prove, you have to negate it first. And you're basically saying, let's say everything else is still true, okay? But whatever you're trying to prove, which should be a natural consequence of everything else, you say, oh, what if that is false? What if this is not the consequence of everything else that I already know? You mix all of them together. And the idea is, if what you're trying to prove, the theorem, if it really is a consequence of everything else that you already know is true, then the negation of that quote unquote should not mix well with what you know is already true. And that's why you get to a contradiction. Yep.
So if you get if you're doing the contradictions, you get something that's false, so that means it's true.
Okay, let's take a look. This is a little bit ahead of time because there will be another dedicated slide on proof by contradiction. But since you guys are asking it and since we are actually using it, instead of having you guys just mechanical doing it, I want you to understand why this works. Okay, so let me just kind of give you this. I think I can use a text editor for this. Okay. All right. So let's just say that in this case, phi is by itself, a lot of expressions. Okay, it's just a lot of stuff that you know is true already. We are asking the question of, does that imply psi? And psi is a theorem. Okay, this is something that you think is a natural consequence of all the stuff that we specified in phi. So I want to make sure that we use the Greek symbols here because each one can be a huge, big, long, well-formed formula. Okay, so they're not single variables like P, Q, R, S. Okay, each one is a huge, long thing. But I don't really care, okay, because I want to show you, okay, so what if psi really is a natural consequence of phi? Then the implication will work. Because whenever phi is true, then psi has to be true too. Okay, if phi is not true, we don't really care because this is supposed to be the natural consequence of phi, but if phi itself is not true, then there's nothing to speak of what is the natural consequence of that. Okay. All right. So let's say this is right. So the question now is, if I introduce not psi into the system and say, okay, let's say that is not true, and phi itself, what does this look like to you? How does it relate to the previous expression? I mean, this is something that's already over there, except I did not use the same names and did not use the right order, but it's the negation. Yep, exactly. So we can manipulate this whole thing, okay, and say, let's put negation on top of negation on top of whatever we have here. So let's see what happens when we do this. Okay. It's okay, right? Because I can actually establish a equality here compared to this thing here, because double negation should not change a single thing. Is that okay? All right, go ahead.
Isn't that showing triple negation?
Well, it's not triple negation because this negation is not applied to not psi, it is applied to the conjunction. Unless I did not use parentheses correctly, let me double check. No, my parentheses are correct. Because this whole thing is a conjunction, so this not is negating the result of the conjunction, and then this not is negating the result of the other not. Is that okay? In other words, I take, okay, let me just put extra parentheses here. Would that be better? Okay. So is that okay? Does everybody understand how these two lines connect? It's just because double negation doesn't change anything. Okay. So the next line, I'm going to use De Morgan's law. De Morgan's law is going to take care of this part here. Okay. So we'll change the negation of a conjunction into the use of an or. So it becomes psi or not phi. Is that okay? It is the result of the application of De Morgan's law. And now I can apply De Morgan's law one more time, or not, okay? Because what I also can do at this point is I can reorganize using the commutative property of disjunction. I can now say, hey, I can mention not phi first, and then mention psi. Hey, not something or something. That fits the form of an implication. Okay, so we have not phi implies psi, hey, I think we have seen this before. The stuff inside the negation. What is that?
The initial one.
The initial one, okay? So that means if the initial one is true, which means psi is in fact a theorem that you can derive from phi, then the negation of that has to be false. And what do we know? How do we represent false? Zero, your false, your contradiction. That's why, that's why proof by contradiction works. Is that okay? Sort of? Yep.
But we could go one way and just rewind, like undo what we did and get back to that, which I think is exactly what we did here. So we do a couple operations and then we undo them, and we obviously will get back to the initial state.
Correct. But sometimes it's easier to prove the contradiction. Like resolution, really lends itself to prove something is false, because you're combining the terms and you're eliminating terms in between. And first of all, it has a upper bound of how many terms you can actually have. And the second thing is it really lends itself to get to the false conclusion. Because when you have a CNF, if one term is false, the entire thing is also false. So that's why proof by contradiction, even though a lot of theorems can be proven either directly using just a forward proof or proof by contradiction, proof by contradiction is an extremely powerful technique for proving because a lot of times it's just easier. And resolution is one of those mechanisms where it lends itself to proof by contradiction. Are we still doing okay so far with all this stuff here? All the items connected. Okay. All right. So this is great. We actually talked about a few things that are not in the notes. I'm not going to ask you guys about those things. This one eventually will be in one of the topics. Proof by contradiction is one of the slides in the future, so we will get to that one too. All right, so any other questions about resolution? No questions? Okay. And as I said, it's the rationale of these things, the why of these things that I think is more important than the mechanical aspect. Because once you understand the why, it makes it easier to understand the what, and then the how is really just mechanical, just details. So we won't have any more stuff on propositional logic, and what I'll do is on next Tuesday, I'll give you a practice exam, including up to resolution, the proof by contradiction stuff. So all that stuff will be in the first exam. But the exam itself is going to be 1 week from next Tuesday. Not next Tuesday itself, but 1 week from next Tuesday. Okay. So approximately, 9 days from today? More than that. 7 plus 5 is 12 days. Yep.
So have the practice exam due by Tuesday so we can go over it, or have it due by Thursday, or you can go over it?
I'm going to go over that in class with you guys.
Okay.
Yep. All right. So after propositional logic, we'll get to predicate logic. But before we do that, it really is helpful to take a look at what is propositional logic so we can contrast these two systems. In this case, let me see where I can find an example. I'm just scrolling through to find an example of the definitions of P, Q, and R and S. I suppose the homework is a good example. So I'll go back to the homework. All right. So when I go back to the homework, you read each variable, and the variable, is just saying, something that can either be true or false, but has no, it's lacking one thing that is really important. It's called a quantifier. Okay, because P as a variable is just saying cisp is a boring class. Okay, that's either true or false. Okay, Tech is teaching cisp440. Now the next one, the other two actually has a quantifier built into it, but I did not specify the quantifier itself, because when I say a gamer is taking cisp440, with a quantifier we can say, you guys already know quantifiers. So which symbol do I use if I want to specify a gamer is taking cisp440? Any, or there exists, okay? Someone sleeps in cisp440, which symbol should I use? There exists, okay? Not for all, because I'm not saying everybody sleeps in cisp440. That would be the for all symbol, okay? All right, so, but this is not taking into consideration of the quantifiers. The next topic that we'll talk about, which is predicate logic, does take into account quantifiers, which makes the logic system a lot more useful. So the first slide is really just explaining that. Okay, so I'll just go ahead and read certain portions of this. Propositional logic calculus is useful, but it has limitations. Particularly, it has no quote-unquote parameters. So what do I mean by a parameter? Well, a parameter, okay, first of all, let's get back to CISP 360, okay, all the way back to 360 or even 300. What do we use parameters for when we handle subroutines? Why do we need parameters?
Information.
Okay, go ahead.
To get an output.
To get an output, go ahead.
I said functions.
But why do we need parameters? What happens when I say, okay, you cannot have parameters in functions, in subroutines?
Transfer information.
Yeah.
Transfer of information. Specify information that is specific to that instance of use of that subroutine. Go ahead.
I was going to say to limit the bound.
Say again?
To limit the bound.
Okay, so the limits of the bound are specific to each instance of calling a subroutine. So it's not universal to all instances of calling the subroutine. Okay, very good. So now we can go back to my homework assignment, because this is a perfect example of parameterizing something. Okay, let's take a look at this one here. CISP440 is a borrowing class. I can parameterize this at least in one way. I can take CISP440 out and turn it into a parameter. So now I can target CISP400, I can target CISP300, because now the class that I'm claiming is borrowing is a parameter. Propositional logic has no mechanism to deal with that. Okay, you cannot say, some class is borrowing, and I'll tell you which class later on. It doesn't have a mechanism to handle that. Propositional logic has that limitation, but predicate logic is designed specifically to overcome that particular situation, that particular limitation. All right. So I use, in this case, I say, tag is a professor. That is a typical thing you can specify in propositional logic, because it's either true or false, but it's not parameterized. In propositional logic, you can now specify, which professor, who is a professor. So that can be true or false, but it's specific to that person, that variable, or whoever is bound to the variable. All right, so let's move on to the next one. The next one talks about quantification or quantifiers and program verification. So let's take a look at searching and why quantifiers are useful. This slide basically talks about why quantifiers are actually useful, because ultimately what we want is automated theorem proving, which is great. But what are we applying automated theorem proving to? Why do we want to be able to prove theorems automatically? Because all the math people ask for that. No, the math people will never ask to have an automated system to prove theorems. Why not? They will put they'll put it out of a job for one, and two, they take great pride in proving theorems. Exactly. So if somebody, let's say a mathematician spent 20 years to prove a particular theorem, get it published, get the field medal, which is kind of the same thing as the Turing Award in computer science, which is the highest recognition. Okay, spent 20 years. Okay, it's great. The entire math society, cheered on and sent him congratulations. It's all over Facebook, Twitter, and whatnot. Okay, and then one day before that, a computer scientist basically put in all the things, let the computer run, and in 12 minutes, the proof is done. Okay? A mathematician would not want that day to come. To have a computer to only spend a few minutes, a few seconds, maybe years, okay? But the point is, you let it run and it just walk away, right? So that request will never come from mathematicians. So who is asking for automated theorem proving? Not mathematicians, very good. But who else? Who else is interested in theorem proving? Yep.
Well, if we go back to your example of like an operating system proving that it's verified, like it's totally secure, you turn that into a theorem, you prove that, then you know it works well, right?
Yep, it's people who want to be able to validate that the program does do what it is supposed to. Okay, and that would be us. It would be us. We are our own customer, okay? Because we don't take great pride in being able to prove a 3 billion line program is correct. I mean, that's just chore. Okay? But we can use the result of that. We can say that, oh, this program works, it works the way it's supposed to, so I don't have to worry a single thing about it. Okay? So we are our own customer. But what do we do when we need to validate programs? One thing that we have to do is to deal with arrays, not just individual variables, but arrays. Okay? When you deal with arrays, quantifiers becomes very useful, right? Okay, let's take a look at the search algorithm, which is what this paragraph is about. So we'll go ahead and take a look at this particular example, and then we'll get to this part here, which is all quantifiers and whatnot. Okay, but we'll go step by step, go slow. Okay, first of all, this is the problem. Okay, the problem is you are given an array A, we'll just call the array A, and a particular value key, k, to find. Okay, and we have other notations to say, okay, the array has this many elements and whatnot. But the general idea is we're just trying to find a value, or determine whether the value is in the array or not. Is that okay? Okay, we have all written algorithms to do that, in cisp440 and other classes. The question is, how do we express whether that the search algorithm is correct? Okay, so let's say the algorithm will give you a result R, okay, and the result R is true if and only if at least one element of the array has the value of k. I don't even care about how you write the algorithm, whether you use a loop or whether you use recursion or not, whether you use pointers or indexing, I don't even care. I just want to know how to express that the algorithm is correct. Okay? But Tab, you just did it. You just wrote everything out in words. Is that okay? Well, it's okay in most cases, right? I mean, you wouldn't go back to cisp400. How many people are taking 400 or 430 this semester? Are you guys going to go back to your professor and say, I want you to specify the expected behavior of the next homework assignment using only math symbols, but you can use quantifiers and whatnot too. You're not going to go back and tell your professor how to express the correct result of an algorithm, right? But in this class, we want to do that, because I don't want any two different ways of interpreting the same thing. We want that precision in mathematical terms or equations. Is that okay? All right. Because I don't want you guys to take my words and go back to Fox or subsidiary and go like, well, text said that you are supposed to give us, the expected behavior in mathematical terms. Where's the for all, where's the Derek symbol in your homework assignment? They may not take it very lightly. No, I'm pretty sure they will take it lightly. Raj would just say, well. And leave it at that too. He would just kind of move on and not even to dwell on it.
Barely even acknowledge it happened. Barely even acknowledge it happened.
Yeah, he was just, well. Now let's get back to our topic, right? Okay, so I got a few sloppy ways to do things, and sloppy ways are not really great because they don't capture the entire algorithm. So, but let's take a look at sloppy way number 1. Okay, R is 1, true, if and only if at least one element in A has a value of k. Well, that's easy to do. The algorithm itself, instead of being a search algorithm, I'm done. It ends up with that result, right? And, oh, by the way, never mind, you know, I need to do that too. Yes, it is found because I just put it there. Is that the correct search algorithm? No. Where's the search part? There's no search in this algorithm, okay? So what went wrong in this case? Oh, I didn't specify that you're not supposed to change anything. Okay? All right. So let's say we have a sloppy, incorrect way 2. Okay, sloppy way number 2. R is 1 if and only if there's at least one element in A with a value of K without changing the value of any elements in A. It is sloppy, but you know it's kind of correct in this case, but it is still very sloppy. So what we want to do is not to be sloppy and make it so that it is very specific and there are no 2 ways to interpret the meaning. And we use a notation. This is new to this class, so I just want to make sure that we understand RA bar is basically the number of elements in array A. It's not really new in this class. We have seen this symbol already, but just not applied to arrays. We used to apply it to what? A set, okay? It means the cardinality. But I can use the same symbol applied to an array, so now it returns the number of elements in the array. Okay? Basically the same idea. All right. So with this, what we'll say is this thing here. This is the correct behavior of the program. Okay? Let me just highlight the portion that is actually the answer, which is only this part here. R equals to, the other part is a shorthand. It'll basically say there exists an integer I such that I is between 0 and bar e bar minus 1 inclusively, such that V of I equals to K. But that is still wrong because I can just change the array and make it meet that requirement. So the second way to do it is to do it this way. This is longer, it has a conjunction, and there are 2 parts to it. One part is exactly the same, or almost exactly the same as before, which is the first part. So if you look at the first part, other than the mistake that I had earlier, which is not having a close parenthesis here, otherwise it's the same thing. The second part of the conjunction is this part here. And how does that work? What is the second part doing? We have seen something like this already when we talked about the behavior or the expected behavior of a sorting algorithm. So what do you think is this part is really doing? Yep. Yep. It's basically giving a name or giving a symbol to every single value before the array as the initial condition of the array. And then the other part only refers to V subscript I, so that we are not going to be able to change it. Yep.
What is V subscript I?
V subscript I is really just variables that are defined in this particular setup so that I can refer to the initial value, the values of elements in the array. Yep.
Are those dollar signs around K of any importance?
The dollar signs.
It probably just didn't translate properly.
Yeah, I didn't hear
The right side of what again?
At the very right.
Middle of the screen on the right.
Like you forgot double dollar
Oh.
signs or something.
Oh, that's my bad.
Yeah.
Yeah, that's supposed to be the enclosement of the content inside the formulae. It's supposed to be dollar, not dollar.
Yeah, there's been every now and again you'll see the dollar K dollar sneak up in some of the online stuff.
Okay. Okay. But it's basically just K, you know, as a variable.
Just throwing money away like that?
When a K here, a
It
K
may be a
there,
negative
it's a lot of
number.
money.
I mean, collecting money. All right, so the second one we have seen already, so I'm not going to talk about this one in detail. How do you confirm an array is actually sorted, okay? So we basically use this, you know, R is a Boolean variable. If R is 1, then the array is properly sorted. And we have an example of sorting. So anyway, this particular slide just talks about why it is important to use there exists and for all. Okay, that is that's part of the language that you need to use in order to specify the correct behavior of an algorithm, or the correct outcome of an algorithm. I stand corrected, because I don't care how you do it. It can be magic. It can be little elves in your computer that is doing all the work by magic. I don't really care. I just need a very mathematical way to say this is qualifying it as the correct result. How it is done, I don't even care. Okay? Are we okay at this point? And if you don't mention your favorite magical being, you can email me, so next time I'll mention that, like unicorns, whatever. All right, so this part talks about predicate logic and propositional calculus and how they are related. What we're doing is we're extending stuff. Okay, we are taking everything that we already have in propositional calculus, but we are extending it so that we can also deal with quantifiers. So the additional rules that we are adding into the transformation set, which is zeta, is this symbol here. This is there exist. Excuse me, this is for all, and this is there exist. But there are inference rules that we have to add on top of what we already have, because if you say that for all x, okay, x in this case is universal, okay? For all x such that p of x is true, then it's really saying the same thing as the other part, which is it is not true that there exists a particular x such that p of x is false. It is double negation, but you can see that I'm applying the double negation not just right before the entire expression, which is going to be trivial. Okay, I am changing also the for all symbol to there exist. Is that okay? Does that make sense to everybody? Intuitively, does it make sense? And then the opposite is also true, because you can just basically apply the double negation in this case. But the opposite is also true. If you can claim that there exists at least one x such that p of x is true, then it's really the same thing as saying it is not the case that for all x, not p of x is true. Okay? It really is saying the same thing. So these two are additional transformational inference rules that we can add to the system to handle predicate logic and not just propositional logic. Are there any questions? Questions? Okay. So moving on. All right, so this part, it talks about, the new stuff or new concepts that we need to add in predicate logic in addition to quantifiers. Predicate logic incorporates functions. Now, what kind of functions are we talking about? The same kind of function that we have been talking about in this class. Okay, so this is not any other function, it's really the same kind of function that we have been talking about. So we have parameters, we have functions, and so on. So now the question is, what other things do we need to add to the language that we are defining? In predicate logic, a formula is recursively defined kind of like the way we did it in propositional logic, but with the addition of the concept of a predicate and parameters. So we will define that a particular predicate P is a well-formed formula, and it has these terms T1 to Tn to specify its parameter. And each parameter can be the result of a formula. So T1 all the way up to Tn, they are not individual variables. They are parameters. Each one can be a formula. Each one can be a formula. So this is really interesting because both of these things did not exist in propositional logic. It is new to us. Okay? The parameterization and also the availability of functions is not there before. The equality of terms is a formula. So basically, you look at T1 equals to T2. T1 is a formula, T2 is a formula. The equality of these two, it can be true or false, is a formula. Excuse me, it is a formula. The negation of a formula is a formula. So if phi is a formula, the negation of phi is also a formula. The connectives, remember, connectives, when we talk about propositional logic, which set do these things come from, the connectives? Omega, yep, omega is the correct answer. Alpha gives us all the constants, variables, and the schematas. Iota gives us all the initial states. It is omega that gives us all the connectives. So if you have a formula on one side, you have a connective, and you have another formula on the other side, this entire thing is also a formula. And then the last one is what we just used in the previous slide. You can specify for all. You can also specify there exist. So in this case, phi itself is a formula. In other words, phi can be something that looks like this. Okay? If phi is a formula, then the quantified formula is also a formula. Is that okay? That's kind of recursive because now you can take a formula that looks like this and put it into a parameter of a predicate. Okay? You can combine it in any possible way based on what we have here. Are there any questions of what is a formula? Yes or no? Are there any questions about what a predicate can be? Predicate, yes, go ahead.
When you said there were questions about what was a formula, you mean like the idea of just a mapping, a set of numbers, set of numbers?
A formula really is doing the same thing as what we know as a well-formed formula in propositional logic. Except for whatever reason, in predicate logic, they don't refer to those as quote-unquote well-formed formula, but a formula in this context is really a WFF. So we are just recursively trying to define, in this particular language, what kind of construct can we create using, the connectives, using the predicates, and using the formulas, using the functions. So now we have to define what is a term. A term can be an element from quote-unquote the universe or the domain or the universe of discourse that each element can be considered a term. So in this case, we don't have a set called alpha anymore. Instead, we have a domain. But the domain is basically the universe of everything that can be here. I'll give you an example later of what is the universe, which is also known as the domain, which is also known as the universe of discourse in predicate logic. A variable is also a term. So an element in the universe is a term, a variable is a term, and the result of applying a function is also a term. And terms can be used as parameters to functions. So you can use the result of a function itself can also be used as the parameter to another function. Is that okay? All right. And because of the use of quantifiers, we also have a new concept of a variable being free and a variable being bound. A free variable is one that is not bound, and a bound one it is not free. So that's kind of a circular reasoning. A variable is bound when a quantifier is applied to it. In other words, you can also call it a quantified variable. A formula with no free variable is also called a first order sentence. In other words, every single variable in a first order sentence is quantified. Is that okay? Okay, let's use some examples.
Professor?
Yes?
What do you mean by a free variable? Do you mean like it just can't be modified, or?
No, it means it's not bound in any way. There's no quantifiers applied to it. Okay, let me give you an example. Okay. X and Y. Both of these are free. because I didn't say for all or there exist. Okay. If I say there exists x such that x and y, then we have one bound variable. X is bound because of the quantification of x. But y is free because nobody told me anything about is it for all y or is it there exists a y. Is that okay? On the other hand, if I say there exists x and then for all y, x and y, then this is now a first order sentence because x is bound by the there exist and then y is bound by the for all. Is that okay? All right. Now, in this case, x it cannot be an element of the, well, x has to be the element of the universe, and this is now my predicate, because I'm trying to state something about x, y, and it can be either true or false. So now we talk about the semantics. Oh, let me go back to the previous one first. Are there any questions about everything here on this slide, up to the bottom of that slide? Questions of any kind? No questions? Okay. I think we'll come up with some examples really soon, so that all of these would be it's easier to understand. I am going to skip the semantics first. Okay, we'll skip the schematics just so that we can get to at least one example to illustrate. Okay, what do you mean by the universe? What do you mean by a predicate, and so on. So we'll talk about the universe. In this case, the domain, also known as the universe, also known as the universe of discourse, are these particular elements. It's a set of these elements. So in this case, this domain is finite. It looks like there's just a whole bunch of names of a whole bunch of people. In other words, this universe has elements, and each element is representing a person. Is that okay? Okay. So the next question is, what is a predicate? The predicate in this case is a P. Okay, P is a predicate, and you can see that I'm using the notation of a function because it is mapping the Cartesian product of D crosses D to true false. Is that okay? So it is a function, and right away we know this has to be a non-surjective. Well, okay, it has to be a non-injective function because the set D cross D is bigger than the set true false. So it cannot be injective because we only have two things to map to, and yet we have how many things in the domain itself, the domain of P, to be more specific. We have, is it 9 names? I think there are 9 names. So 9 times 9 is 81. So we have 81 elements in the domain. We only have 2 elements in the codomain. So that is enough reason to tell you that, hey, this is non-injective. Yep.
So if you look at the cross product of like the set D and D, so would, like, for example, Mary and Mary be in that set?
Mary will also be in that set.
So it's
Right.
9 times 9, not 9 times 8.
It's 9 times 9. That is correct. Yep. All right. Now, now we basically said I'll give you examples. So John Paul coming from the domain maps to true. John Kenneth maps to 0, and so on. So this this will have 81 entries. Okay, there are 81 entries in here, basically saying how people relate to each other. And P, for example, is defining John is the father of Paul. Okay, John is not the father of Kenneth, and so on. And this set corresponds to the predicate P, and it has 81 elements. This particular set has 81 elements. We talked about that already. And then we can define Q and define R. So Q here is the mother of, and then R is an ancestor of. So we want to make use of Q, P and Q in order to define R. P is a predicate, Q is a predicate, and R is also a predicate. So predicate simply means that it can relate elements in the universe so that you can say, okay, this is either true or false. Is X the father of Y? Okay, it's either true or false. Is X the mother of Y? Is either true or false. Is X an ancestor of Y? That is either true or false. Okay, so each predicate is trying to give you an answer, of okay, are these things related in a particular way? In a particular way. So we want to define R, okay, and based on what we already know about P, and based on what we know about Q, you can probably come up with R as one huge function, right? Because all you have to do, how many elements will be in R, by the way? R is also trying to define ancestor of, so it's trying to identify a variable is an ancestor of another variable. Is that right? So we are still talking about D, Cartesian product D maps to true, false. So how many elements do we have in this case in R? 81, exactly. Yep, go ahead, you have a question.
So the variables in this case can use to define the most basic facts.
Because these can, there's nothing else that can define P or Q.
What is M?
What is M? That is a good question. I think M is the overall system.
Is it on top of it?
There we go. The collection of all functions and predicates is called an interpretation. It is denoted as M. So it's because we skipped the previous section that we did not get to see what M is. But M is the collection of all the functions and all the predicates. And as a result, M has to start somewhere, okay? So in this case, I can start M with, defining who is the father of whom and who is the mother of whom. But R doesn't need to be defined explicitly. In other words, I don't need to spell out everything with R, because what I can do is I can define R using this particular way, okay? So we will take a look at this thing here and try to figure out what it is really saying. The first thing we notice is it is a first order sentence. Now, how do I know this is a first order sentence?
Because all the variables have a connector,
a quantifier. Okay, very good. I know what you mean. Okay, so that's good. So it is true. Okay, every single variable has a quantifier applied to it prior to the use of that variable. So let's check it out. Okay, because we have, by the time we get to this x, the use of xy in a predicate, x and y are both quantified. By the time we get to the use of this z, x is quantified by this x here, by this for all x. Z itself is quantified by this there exists. So this is a first order sentence, which is good, which is really important. Okay? Okay, now that we know this is a first order sentence, let's try to interpret the meaning. Okay, the outermost part, everything is inside these two quantifiers. So it's basically saying for all x in the universe, which means for any x in the set, for all y in the set, the following should be true. And what has to be true? So let's pick out this one first, okay? This is one disjunction. It's saying that x is the father of y or x is the mother of y, because P is father of and then Q is mother of. Okay, so that means if this expression is true, I don't need to look at the rest. Is that okay? Because this expression, this disjunction, is also connected to the rest using another disjunction. So that means if I can establish directly that x is the immediate ancestor or a parent of y, then I can conclude right away that x and y are related by ancestry. Is that okay? It's not common that we refer to our father as an ancestor or our mother as an ancestor, but if you look at the definition of an ancestor, it still applies. Okay? And then if you look at this whole thing, this part here, this entire thing, is saying it is equivalent to R, which also means if this entire thing is true, R, X, Y should also be true. If this entire thing is false, R, X, Y should also be false. That's what it's saying. We are defining the predicate R using the other predicates that we have already defined. Okay? Okay, so the first part is pretty easy. It simply means, if X is the father or mother of Y, X is an ancestor of Y. Okay, that works. What if this expression is false? What if X and Y are not directly connected? What if X is a grandma of Y? Yep.
Then wouldn't R be false as well?
Sorry, say again?
Wouldn't R on the other side be false as well?
Not right away. We have another chance.
Alright, so that's another chance.
We have another chance. Okay, the other chance is the other side of the OR, which is this thing here. Okay, so let's check out what this is really saying. So this means, there exists a Z, okay, in the universe, okay, in the domain out of those 9 people. There exists a person out of those 9 people, such that I'll just combine these two as one, so that X is either the father or the mother of Z. This is a new person, okay? So we establish one parental relationship, and then we recursively use the ancestry relationship. In other words, we are basically saying X can be the father or the mother of Z, and Z is an ancestor of Y. Well, what is that going to tell you? X is an ancestor of Y. So we are recursively using the R predicate to define R itself. Are we sort of doing okay with this? Okay. Yes? Go ahead. Yeah, go. No. Okay. No questions about this? Okay, remember the 3 types of questions: the how, the what, and the why. Okay, so the how is not really, the how in this case is really, do we understand the expressions? Do we understand the formula? Okay, do we understand the quantifiers? There exists for all and so on. Are we okay with that? Okay. Then the next question is, what is this? Okay, let me just highlight the entire thing. And then I'll ask the question, what is this? And you have to read the paragraph before, on top of this one. We're trying to define R. We're defining a predicate R using the predicates that we have already defined, which are P and Q. That's the what, okay? So the most important question is why, okay? Why are we dealing with this? Specifically, why are we dealing with the definition of a predicate that is not spelled out? Instead, it is defined by some kind of a formula. Well, first of all, okay, sometimes it's easier. You don't have to spell out all 81 elements of R, of R. And then the second one is, this really expresses the relationship of ancestry. Okay? And the third reason is really simple. We want a computer to be able to deduce. Okay? You just have to enter into the system who is the father of whom, who is the mother of whom, and how do you define ancestry recursively. Then you can ask the question and say, tell me all the ancestors of blah. And the system will go through everything and tell you, okay, all of these people are ancestors of that particular person. Or vice versa, you can say, give me, this is the ancestor of whom. You type that in, and then the system will automatically give you the descendants of that particular person. So we want it to be automated, okay? Can someone tell me what programming language makes use of what we have already talked about at this point and actually do it? Because such a programming language exists. It starts with a P, but there are many, many programming languages starting with a P.
Prolog.
Prolog, very good. How do you spell prolog? Without the UE.
Yeah.
Yep, exactly. So Prolog is the programming language that can do this. It's a very interesting system. Go ahead.
Will any of this be on the test, the predicate logic stuff?
No, the predicate logic is not going to be in the test. Somebody just sent me a message. Ignore. Okay. And this slide doesn't talk about it does talk about prologue. Okay, so I have, okay. So let me go through this example because some of you may actually like it. There we go. All right. So in prologue, you can make statements. Okay. So in this case, the universe would be all the things with lowercase. Okay. So the elements in the universe would consist of Obi-Wan, Luke Skywalker, and let's see what else. The green hack, blue classic 3. These are all going to be elements in the universe. Okay, so there are 4 elements in the universe that I can identify. And just looking through it, make sure there are no more. Okay, there we go. Okay, so there are 4 elements in this particular universe. This is a predicate. And remember, a predicate is really just mapping either Cartesian products or really just the universe to either true or false. So this one is directly mapping Obi-Wan is a Jedi, is the predicate, Obi-Wan is the parameter. That is by definition true. Okay, I'm just defining, okay, this is true. I'm also defining Luke Skywalker is a Jedi, is also true. So these are known facts, okay? I'm starting out with known facts. And then I define another predicate, but this time it is not spelled out. This time, it is, okay, how do you read this stuff here? What do you think?
Can use a
next paragraph actually tells you, but.
Can use a lightsaber, or implies that.
Can use lightsaber is implied by is a Jedi, with X being the parameter. Is that okay? And there is an implicit quantifier for all. So if you read this part here, and then you read this code in prologue, and then you read the actual interpretation, this is what it's really saying, okay? But in prologue term, it is saying for all X in this entire universe, if X is a Jedi, it implies X can also use a lightsaber. That's what it's saying. Is that okay? All right. So we'll move on to the next rule. The next rule establishes ownership. Okay. So this is just a predicate. It is one definition of the predicate owns. Okay. So the universe consists of Jedis, characters. It also consists of lightsabers. So in this case, green hack is the name of a lightsaber. For those of you who actually watched the movie very carefully, the first lightsaber that Luke Skywalker used when he was practicing in the Millennium Falcon, remember that? It's blue. It's green in color, and it was a hack job too.
It was a Graflex. It's a Graflex.
It wasn't
flash
proper.
handle on it.
I think he didn't use the correct crystal, so it's a hack job. Okay, so Luke Skywalker owns, in this case, green hack. Okay, but it's an established fact. Okay, so I'm establishing specific elements in that particular predicate. So the second one, says Obi-Wan owns blue classic 3 because the color of Obi-Wan's lightsaber is blue. Okay.
And the serial number on it's really low, so it's rare.
It's rare. It's classic. Yeah. And then I specify, what is green hack? Green hack is a lightsaber. Blue classic is also a lightsaber. Because remember, the universe consists of everything that I need to mention. Okay, so I have different kinds of stuff that I need to include into the universe. So one way to help filter, what is what, is to include additional predicates. Okay, so it's a lightsaber is a predicate that is the only purpose, just like it's a Jedi, is to help me filter and find out what applies to some of the other predicates. Okay. All right. So now we have this rule here, okay, this one is a first order sentence because all the variables x, y are both quantified with for all. So what this is really, but the new question is, what does the word, the comma, that's the punctuation comma really mean in this case? Okay, so let's take a look. Is a proper Jedi 1 is the name of the predicate. And then the elements on the other side is a Jedi owns a particular lightsaber. Okay, so what is the relationship? Is an and, okay? All the commas are basically saying and. So the way you read this is X is a Jedi and X owns Y, and Y is a lightsaber, which basically means a Jedi owns a lightsaber, okay? Implies that X is a proper Jedi. Okay? Because there might be Jedi who have lost their lightsaber or sold the lightsaber to a pawn shop or something like that. So those would not be proper Jedis.
Gotta get that other crystal.
Okay, but wait, there's a little bit more. There's a little bit more, because I do want to finish this whole thing. Okay, so in this case, I have is a proper Jedi 2 as another predicate. And this one says, X is a Jedi, Y is a Sith, X hates Y. So that becomes another qualification to say it's a proper Jedi. And, okay, and then we have this one here. What about, a particular person who is, Sith tolerant? How do we define that? Y is a Sith, and X does not hate Y. Basically, that's what it's saying. Okay, so we'll play with this on next Tuesday. Okay, so on next Tuesday I will finish up the homework assignment. I'll give you the key to the homework assignment. We'll play with this in actual prologue so you can see the answers, and we'll also talk about the practice tests.
Depends on But surprisingly,
Two?
You just love the way it makes it logic. This stuff reminds
You guys have it's like
No, the show was
camera flash bulb is what the original prop used for Luke Skywalker's lightsaber. Flash bulb. So that's why I said, it's a graphic. The handle was the original prop that they made the lightsaber.
I hated the early.
It is a hack job, which is why I just thought that was
very much of a hacker.
Thank you.
I'm okay. Had a good nap. Needed that.
Power nap. Sounds like what, 8 or 10?
Today I actually came in and my morning class is canceled.
I'm gonna say yay.
Yeah.
As long as you found out before you gave it 50.
Yes.
Not
Yes.
S. Otherwise that's
So I came in at noon today, and I'm